Hello, I'm Carole Bernard. I'm going to present some recent work on risk management. In particular, I would like to present work on assessing model risk on dependence in high dimensions. This problem, in fact, arises in many situations in the industry. You can think of it as you have D-dependent risks, and you want to assess the risk of the aggregate risks. And regulators all around the world recognize, all of them, that it's hard to aggregate risks, and there's a lot of model risk when it comes to modeling dependence. So specifically, what we do here is we propose a model and we propose a method to model uncertainty on the risk assessment of an aggregate portfolio. You think of it as a sum of D-dependent variables, and what we want to do is take into account all the information that's available in the market, and then being able to say what is the maximum risk and what is the minimum risk that this risk measure of the portfolio sum can take. We're going to propose two methods. One of them is fully non-parametric and can be used just using your available data that you have. The second method is in the second method, we propose some analytical expressions for the maximum and the minimum of this risk measure of the portfolio. And this work has several implications. Two important implications, I think. One of them is the fact that the current value-at-risk-based regulation, thinking about Solvency II, Basel II, are based on value-at-risk at very high confidence level. And what we show is that if you try to estimate value at risk at very high confidence level, it's subject to very high model risk. And it's even worse than that. We find that kind of a surprising result is that even if you develop a very sophisticated model to model the multivariate dependence, what we find is that if this multivariate models covers, let's say if your data available covers 98% of the space, still these unknown scenarios that you have in 2% of the space will have a huge impact on the value at risk. The second implication, which is also important, is to say, okay, value at risk used in the market are subject to very high model risk. But there are risk measures that are not as subject as the same model risk on dependence, and for which it is actually a meaningful task to develop accurate multivariate models. And one of them is the variance. So let's formalize a little bit the problem. I'm going to assess the portfolio sum. So I'm going to talk about the portfolio sum, which is an aggregate risk where you take the individual dependent variables and you sum them, x1, x2, xd. I'm going to choose a risk measure. So in the first part of the podcast, I'm going to focus on the variance. Variance is a very useful risk measure, and it's still used a lot in portfolio management. The second part of the podcast is going to focus on value at risk. It turns out that value at risk is, of course, more complex, in particular when it comes to assess model risk, but that the techniques needed to assess model risk on value at risk are actually the same as the techniques to assess model risk on variance. So it's actually useful to first understand the simple case, which is assessing model risk on variance, and then move to the more complicated case, which is assessing model risk on value at risk. So you take your risk measure. Let's assume here, for our purpose, that it's the variance risk measure, but you can take another one. Now, we want to fit a multivariate distribution, x1, x2, xd, and then what we can do is just compute this risk measure. That would be a statistical approach. You get a risk measure, and you may just find confidence interval, but you have one value or a small interval of values of this risk measure within a model. In fact, what we want to say is to assess is how wrong we can be, how about model risk behind that, because we choose a risk measure, a multivariate distribution here. So if we take this risk measure to be the variance of the sum, what we're going to do is to find out what is the maximum variance and what is the minimum variance. So this is going to be the minimum variance over all the sums, all the aggregate risks. such that we take into account all the available information. One assumption I'm going to make is that we know very well all the individual risks. So x1, x2, xd are dependent, but we can observe a lot of data on each individual risks. So the marginal distributions are going to be known. But I'm going to focus on dependence information and the fact that in practice it's very hard to get full information about the dependence, whereas it's easier in general to fit a marginal distribution. So here is the setting. We assume the marginals are known, and to start, I'm going to assume that dependence is fully unknown. So the only information you have is coming from your individual risks. And it turns out that even this problem, knowing only marginals and nothing on dependence, is challenging as soon as you have more than 3 risks in your portfolio, or you try to aggregate 3 dependent variables. Puccetti and Rischendorf in 2012 have developed an algorithm that is actually useful to approximate the minimum variance. And it turns out that this algorithm is also useful after being adapted to find bounds on value at risk, and this was developed recently by Paul Embrechts, Giovanni Puccetti, and Ludger Rischendorf. We will illustrate that both of these algorithms are developed in this situation. The fact that marginals are known and dependence are fully unknown comes to the problem that the bounds are generally very wide and sometimes too wide to be of any use in practice, except saying that there's a huge model risk. And one of the reasons is that it ignores all the information on the dependence. So our idea is, how about incorporating in the natural way the dependence information that we can get from the data? And that's our answer, and I will present how to extend that. But before I go to incorporating dependence, I want to review their work and show the case to explain the method when marginals are known and dependence is fully unknown. So to do that, I'm going to use a very simple example. It is not realistic, it's just a toy example. In general, you know your marginal distribution, x1, x2, x3. And saying that you know them would mean that you have a lot of observation for x1, a lot of observation for x2, for x3, or at least that you have fitted a model for your marginal distribution or use the extreme value theory, but you know distribution for the marginals that you trust. And from this distribution, you can simulate as many elements of, like as many observations of x1 that you want and as many observations of x2 that you want. So we put this information. x1 is put into a column. These are the values 1, 0, 4, 6. I'm assuming that I have only 4 observations. So that's where it's really unrealistic. And in general, and our method works actually very well in high dimensions. So you can take more than 3 risks. You can take 30, 500 risks. It will still work. And you can take millions of observations and consider a matrix which will be 1 million by 30, 60, 100. So this example is voluntarily small so that you understand how the method works. Each column, the values in the column, represents the marginal risks. So 1, 0, 4, 6 are the 4 values taken by x1. You can think of it as x1 as a distribution that takes 4 possible values with probability 1 over 4. How do we see the dependence here? We see the dependence how each column interacts with among each others. So, for instance, when x2 is 6 here, we see that x1 is 0, so they are moving kind of in opposite direction. And we're going to fix the marginals, which means we're going to fix the values within each column, but we're going to shuffle the columns. Shuffle within a column so that the dependence change, but the marginal stay the same. So how do we do that? This is an example where we start from our matrix and we shuffle them by order them from maximum to minimum in each column. So I take exactly the same values, just order them. And then I compute the sums. These are the original sum that you would get in your data, but if you trust only the marginals, you're only trusting what is in the column, and you don't trust how the columns interact among each other. Now here, it's another organization of the columns. And this is what we call the comonotonic scenarios. They are ordered in the same direction from maximum to minimum, or they can be ordered from minimum to maximum. It wouldn't change. And what we observe is that the sum, in this case, is actually the scenario that would take the maximum variance. So the sum here takes 4 values, 16, 10, 3, and 0. And if you calculate the variance of this random variable, which takes 4 values with probability 1/4, you calculate its variance. It is the maximum variance that you can obtain by fixing the marginals and like changing the dependence among all possible dependence structure. So aggregate risk with maximum variance, extremely easy to get with your data. Just order them, calculate the variance. And that's the comonotonic scenarios. Now, how about finding the minimum variance that we can get within our data sets by playing on the dependence? So if you have only 2 risks, this result is actually known for a long time in the 1950s. You have 2 risks. The minimum variance is obtained in the antimonotonic scenario. What does it mean? It means that the values taken by x1 are exactly in opposite order as the values taken by x2. So the variance in the antimonotonic scenario when x1a is antimonotonic with x2, so the values are in opposite orders, this is minimum variance compared to the variance of the sum. So that's the scenario that minimizes variance. That's a scenario that has the lowest correlation. Now, how about in d dimensions? If we think about it, so d dimensions, extending antimonotonicity, there's a problem, already with 3 dimensions. If you have x1, x2, x3, and x1 and x2 are negatively correlated, x1 and x3 are also negatively correlated, which means when x1 goes up, x2 goes down, x3 goes down. So x2 and x3 are going down together, which means that they are positively correlated and not only antimonotonic anymore. So in 3 dimensions, we see that it's very hard. We cannot be negatively correlated pairwise between all the variables. So the trick is, and that was proposed by Puccetti and Rüschendorf in 2012, to use the rearrangement algorithm on the original matrix and construct a dependence that has the minimum variance. The way you do that, you think about the sum as you have d dependent risks. You take 1 risk and then the d minus 1 remaining risks. And what we know is that 1 risk is antimonotonic with the d minus 1 remaining risks. So this xKa is antimonotonic with the sum of the others. When you do that, after each step, so you take each column, you reorganize the column so that the values in the column are antimonotonic, which means in opposite order to the sum of the other columns. And at each step, by doing that, we know that when we have 2 risks, it decreases the variance. It's actually obtaining the minimum variance for 2 risks. So at each step, it minimizes, like you get the variance minimized. And you do that for each column until each column is antimonotonic to the sum of the others. Now let's illustrate it on the example, and you'll see it's not that complicated. First column is here, 6, 4, 1, 0. And what I do, and you can start with any configuration. I start from the comonotonic configuration, but another configuration would be fine. So you take your first column, and I'm going to rearrange it so that it's antimonotonic with the sum of these 2. These 2, the sum are 10, 5, 2, and 0. They are here. To make the first column antimonotonic, I'm going to look at the maximum value of the sum, and I'll put in, at the same level, the minimum value of x1. So the 0 is going to come here. In front of the 5, I'll put the 1. 2 becomes 4. 0 will be the 6. And you see here, it's exactly 0, 1, 4, 6. And this is in opposite order to these values. And you do that for the first column. You then do that for the second column and the third column. And that's what happens. So the second column is reordered by looking at the sum of x1 and x3. So you sum this column with this column, you obtain this. And the maximum value of the sum is 6. You need to put the 0 there, which is still there. The minimum value is 3. You need the maximum value here. So the 6 is going to come there. And you do that for each column at a time. And at the end, So you do for the first column, the second column, the third column, and then you redo again. You check on the first column, and then we find that the first column is already antimonotonic, the second column is antimonotonic, the third column is antimonotonic. At this point, we cannot improve it anymore. The rearrangement algorithm is finished. Now, what about this configuration that we obtained here? What is special about it is when you compute the sums. So now, look at this, x1 plus x2 plus x3, you compute the sum, they are all identically equal to 7. What you get is a sum equal to a constant. We know that the variance is equal to 0. And the minimum variance of the sum is then equal to 0. This is the ideal case where you can find a dependent structure where, keeping the marginals, you make them sum to a constant, and that achieves the minimum variance. This is called complete mixability, and there's some theoretical work on it by Wang and Wang. So how about the theoretical part? The analytical expressions are given here. On the standard deviation, what we found is that the standard deviation of the sum is always between 0 and the sum of the standard deviation, which is obtained in the comonotonic scenario. If we illustrate it, and I'm going to use this only as an illustration, with 20 normal and 0, 1. So imagine that you have 20 risks. They are all normally distributed with a standard normal 0, 1, which in practice usually you won't have that homogeneous risks, and the normal may not be that relevant. But to illustrate the study, it's a good example. The standard deviation of the sum of 20 normal distribution could be either 0 or 20. 20 if they are all correlated with correlation 1, so all positively correlated, that's the comonotonic scenario. 0 if, for instance, you put x2 equal minus x1, x2 will still have the right normal distribution, x4 equal to minus x3, and so pairwise, you can make sure that they compensate each other so that the sum is identically equal to 0. And if the sum is identically equal to 0, it's a constant, the variance is equal to 0, and you can achieve the bounds. So these bounds not only are attainable, there exists a dependent structure with fixed marginal that will achieve both bounds 0 and 20. They are also what you can observe really wide. What it says that if you trust only the marginals and nothing on dependence, your standard deviation is between 0 and 20. So our idea incorporates more information on dependence that we have in the data so that we can reduce these bounds. Why is that? If you have two risks, for instance, that are normally distributed 0, 1, and you observe that your data set looks like that, it's actually not that hard to check that they are independent, or at least to check that dependence cannot be rejected. And what I'm plotting here is a square, which is, it could be a circle, it could be another shape. To make it simple, I make it a square, and I put it into a 96% quantile of the normal and a 4% quantile on this side. So I have this square. Within this square, I have most of my data set, most of my observations are here. I fitted the independence between x1 and x2. But it's based on my data set. It's based on my observation. So in this area, maybe I can trust that this is the independence copula. However, if you look at these corners, you have no information at all. It's not possible using the data to say that in this area, you should get the independence copula. And when you fit the independence copula, you only use the information coming from the data. So you can't say that here it's independent. And we're going to define an area F, which is this square, which is defined as x1 being between its quantile at 4% to this quantile at 96%, and x2 being in its quantile 4% and 96%. It's just a convention. You can choose another area F, and we're going to say that we know the dependence because we have enough information in the data to say that we can trust our multivariate model in this area. And we want to solve the problem again, finding bounds on variance, incorporating this dependence information. We know the marginal distribution, so the same setting as before, but now we know the joint distribution conditionally on belonging to this area F that you've seen on the previous slide. We also know the probability to be in this particular area, which will be the number of observations that will just fall in this area, divided by the total number. Within this problem, we solve our original problem, which is assessing model risk. If we know only the marginals, that means that the area where we trust the multivariate distribution is empty. And this setting will incorporate the previous setting. But what we want is in this general setting, finding bounds on the variance such that the vector not only satisfies a given marginal distribution for x1, for x2, for xd, but also a given multivariate distribution on the area F. So when we look at a matrix, the problem becomes extremely simple. And again, I take an example that is a toy example. You will have a much bigger model. And even if we take the normal example that I've presented before, you will have a much bigger matrix. Here, I have only 8 observations. And 3 observations that appears in gray, these 3 observations are exactly falling in this gray, in the red square, where you trust the model. If I trust the model, it means that I trust the dependence. If I trust the dependence, that means I know that when 3 happens here, 4 happens here. The dependence is the interaction between the columns. So this gray area in my algorithm is going to be fixed. I cannot change it. Now I can play with the dependence only outside the area. So outside the trusted area, these are the 5 observations that falls outside the trusted area. And I can reorganize it. Now, exactly inspired by the same technique as before, I can find the maximum variance by putting all the observations that were outside the trusted area in the same order. So that's the comonotonic scenario. And that will achieve the maximum variance for the sum. And here, we haven't changed compared to the previous information on this matrix. We have just kept these 3 rows fixed. And they are just here. We can't do anything. We fix the marginals, we fix the dependence. Everything is fixed. So the sum that we obtain by summing here are sums that we trust in some sense. So we trust them, we won't change them. The only thing we can play on is this, and that's the maximum variance where you use these sum fixed, and then the ones that you obtain by maximizing the variance by putting the comonotonic scenario on the area where you don't trust the model. Now, how about the minimum variance? You apply the rearrangement algorithm that I presented before, but you apply it only on the submatrix where you don't trust the model. So you apply it on this matrix, and after a few arrangements, what we find is that they all can sum to 5. So there exists a dependence in this sub-area that makes everything equal to 5. And then you can compute the minimum variance by taking the variance of the sum, where the sum takes 3 values that are fixed and 5 everywhere else. So now the minimum variance is not anymore 0. It's equal, actually, here in this example, to 2.5. That's because we have this trusted area where we cannot reduce the variance, because that's the variance observed in the dependence, by the dependence that we trust. So I redid the example just so that you see if you have 20 normal and 0, 1, and you fit a model that is independent, so like the graph I presented with 2 normal 0, 1. Now I have 20 of them, so I have a 20-dimensional cube where I trust that they are independent. The probability of this 20-dimensional cube is called PF. And depending on how big is the cube, this is a 20-dimensional cube, and this F is my trusted area. If beta is equal to 0, it's actually the quantile at 0 and the quantile at 1. So this covers the full area. That means that you fully trust the model. There are 20 independent normal 0, 1. If you compute the variance, it's 4.4. Now, if beta is 50%, then F is just 1 point. So it's like you don't trust anything, and you find back the bounds 0, 20 in the case where uncertainty is everywhere except uncertainty is everywhere. The only thing you know is that the marginal distribution are n0, 1. Now, what happens if you add information? So now we're going to do the 2 intermediate case where the probability PF 98% means that the probability that the observation is within the trusted area is actually 98%. So you have 98% of your data set that is in this middle area where you trust the dependence. In this case, if you compute the minimum variance and the maximum variance, you see there's still some uncertainty, of course, because you can play with the dependence outside, but there's a small interval, and you reduced a lot the uncertainty compared to the 0.20 that we had before. So what we find is that model risk on the volatility of a portfolio can be reduced a lot if you incorporate dependence information, information on dependence when you assess this model risk. We also have a formula, which I'm not going to spend much time on it because it's kind of complicated and you can look at the paper for that, but we have analytical formula to find the minimum variance and the maximum variance, and they are obtained as the variance of a mixture between the sum where you trust the distribution and a constant in the minimum case, or a comonotonic variable, which corresponds to the comonotonic scenario in the maximum variance case. But more details are available in the paper. Now, to conclude this first section, I would say that this full method is based on assessing model risk for the variance of a portfolio with given marginals, but partially known dependence. I illustrate everything with the variance measure, but you can use the t-var, or expected shortfall, or actually any measure that respects convex order. But you cannot use the technique that I presented right away with value at risk. There are still many challenges that we are working on how to choose the area, how to modify, for instance, if you don't have enough observation, how to amplify the tail of the marginal if you don't trust the marginals and you want to make more tail risks. So there are some ongoing projects on how to improve this method and make it more practical. In the second part of the podcast, I'm going to develop the one like how to assess model risk on value at risk. What I said what I presented there cannot apply directly to value at risk. And one reason is that the maximum value at risk is not obtained by the comonotonic scenario. So already we know the maximum value at risk will not be the same. And it turns out that the minimum value at risk is also not obtained when it's just a constant. But there are very strong connections between making the variance as small as possible and optimizing the value at risk. And we'll find that completely oppositely than the variance conclusion, we find that the bounds on value at risk, when you estimate value at risk at very high confidence level, even if the trusted area covers 98% of your space, you will see that the bounds do not change. It's the same thing knowing only the marginals or knowing the multivariate distribution almost everywhere, in the sense that 98% of the space is covered. So to conclude, there are a few, I would like to acknowledge a few institutions who have supported this research, essentially the Society of Actuaries, but also a research project I did with Stephen Van der Velde for the Canadian Institute of Actuaries, a project that is funded by the Global Risk Institute, and NSERC that funded my research. More information can be found in a lot of publications or working papers that we're working on, and you're welcome to contact me to get more information on it. Thank you very much.